Alright, in this video I want to derive the elastic potential energy that's stored in a spring when it's extended or when it's compressed. And then I'm going to do a simple problem related to that elastic potential energy. So, imagine we have a wall with a spring and some object attached to that spring, and the spring is sitting at its natural length L. What I want to know is how much energy is present when I take this object and I pull it this way with some force through some distance d. Okay, so we're going to take it from there to here. And so that spring is going to get stretched out. How much potential energy is stored in that situation? Now, we'll recall when we do this, whenever we're trying to find a new energy term, we go back to our work formula. Work is equal to force times displacement. And so if I move from location 1 to this other location, and the spring was at its natural length, I think we can see that this d is also equal to the amount of stretch that the spring will experience as it is pulled out. And so first of all, we can start by simplifying this equation to work is equal to force times elongation. And that would work equally well if instead I compressed the spring from its natural length by a distance d. Then we would see that the difference between the natural length and the current length is still delta x, and delta x and d are the same thing. So pull or stretch, however much we move this object from its natural length, that's the definition of compression or stretch. Now for the force, we have a little bit of a complication here. Force for springs is equal to kx. The problem is then that when I pull the spring from here to here, I get one force, force 1, and then when I pull it from here to here, this next section, I get some other force, and then you can even imagine a third section where I get it out and it's F3. So the point is the force is constantly changing as I'm pulling this spring out. If I plotted the force as I pull the spring out to a stretch of delta x, I would see that it actually changes as a straight line. And that's Hooke's law, and that shows that it's linear. So when I initially started pulling the string, I wouldn't be doing much work at all because I'd have very little force to work out. Here I'd be doing a medium amount of work, and here I'd be doing a lot of work because my forces become quite large that I'm pulling against. So how do I handle that? Well, I want to get the effect of that force pulling out over that whole stretch. And so I can view this as the area under the curve, just like I would have with a velocity time graph, velocity time graph that's going up like this. If I wanted to know the total distance traveled, I could imagine breaking it down into tiny sections where I find the velocity times the time at that spot, and at that spot, and at that spot, and 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 add them all up. And I would get that the area under the curve is equal to the distance, which is equal to the velocity times the time for all those different instances. So 1, 1, plus 2, 2, plus 3, 3, right? This little cube, and this little cube, and this little cube, and this little cube, plus off into infinity would give me that total area, or my total displacement, if I viewed it as a bunch of little displacements. You could make the same argument here. Force times delta x gets me this one. Force times delta x gets me this one. Force times delta x gets me this one. But if I want to represent that area with just one value for force instead of doing all these little things, since it's linear, what I can do is I can use the midpoint. And if I imagine graph number 1 as a straight line, and I imagine graph number 2 as using the midway point, then the total amount of work or force experienced over distance, or the total amount of work for these two scenarios, are the same. The area of this triangle is equal to the area of this rectangle, assuming that this is at the midway point. So, if I want to get a representation of force, what I need to do is I need to take the halfway point of the force throughout all of the changes. If it starts at 0 and it goes up to this value, which if I use the equation I can say if it's at delta x it's k delta x, then the midway point should be 1/2 k delta x. And so if I imagine that's my average force, then I can get a representation of how much force I have where I use too much force for my initial pulls and too little force for my final pulls. And so my average force represents a good amount for the whole thing. So that's going to be AVG. So that's going to be 1/2 k delta x times my delta x, which is going to be 1/2 k delta x squared. So that's the work to pull the spring from this location to this location. Now, anybody that's watching this video that studied calculus knows there's a much better way to approach this, where you view this as the integral, but the course that I'm making this for, most of you haven't studied calculus, so I'm just trying to make the argument that if you have this changing force, instead of trying to worry about what it is at all these different values, you can simply use the average value to represent the force as you go through. So if that's the work that you have to do to pull it out there, we can view that as the potential energy or the elastic energy associated with changing from 0 to delta x squared. So what does that mean? Well, let's say we have a spring with a elastic potential of 12,000 Newton meters per square Newton meters. Then we extend it 1.4 centimeters beyond its equilibrium. What's the elastic potential energy? So E here is going to be equal to 1/2 k delta x, that would have been the average force, times the distance that it would have gone through, which would have been another delta x, so that becomes delta x squared. 1/2 12,000 Newton meters. Delta x, careful here, we need to be in meters. And we can get a value of 1.176 joules. Question also says, how would it be different if it was a compression instead of a stretch? Note here that the elongation or the compression is squared. So the answer is, how is it different it's compressed? The answer it is not different at all. If 0.014 had been negative 0.014 when we squared it, we would not have been able to tell the difference. So, to find the work that was done to stretch the spring, we use the force times the displacement. We have a changing force, so since it's linear, we can represent a changing force by an average force instead. The average force is going to be 1/2 k delta x, because it went from 0 to delta k delta x, so the average is 1/2 of that. So 1/2 k delta x times the distance you pulled it through, delta x, gives you 1/2 k delta x squared. That is equivalent to the elastic energy. And here we can substitute those all in and see, despite the fact that we have a pretty big spring constant, we get a pretty small amount of energy because we have delta x that's kind of small and we squared it. So that's the formula for elastic potential energy. In the next video we're going to do an example where we combine that with other forms of energy to solve a more complicated problem.